Swayam Prabha. Digital India. Educated India.
Good morning, everyone. Welcome back. And today's lecture, we are going to really cover two major aspects on granular meter modeling. And one is how to model deformable granular matter. The other is how to model grain crushing. So, in a sense, that the modeling of both aspects are pretty challenging. That's why I'm going to introduce what has been done in our group in the past years. We address the two challenges here. And so first, let's see that how we can model highly deformable granular meter. Here, I put an emphasis on highly deformable, rather than because as we introduce DM in a sense that we assume a slightly deformable particle. We allow certain small deformation, and then the overlap will generate a contact force. But here, this is the different issues that we consider basically that this granular matter are deformable. I'm going to introduce the background first, and then introduce different ways how we can address it. For example, I introduce multi-particle FEM modeling, and also introduce total Lagrangian speech modeling of this deformable matter, and then address coupling with other thermomechanical coupling for the powder metallurgy, and also for densification in a sintering process here, right? And so first, let's introduce the background here. So highly deformable granular matter widely present in a lot of industrial and engineering processes. For example, in the pharmaceutical manufacturing, that when we manufacture the tablet, and then normally we compact the powder together to make a tablet here, as I show here, and also in a powder metallurgy, and in many situations that we basically we heat the powder or something in a high temperature, and then we compact it, and or we sintering it, and this is another way that we do it. And then in the ceramics, and we can really to compact the ceramic powders to make a ceramics product here, right? And then in the battery industry, and the lithium battery electrode, and these are the other thing that are we need to understand their thermochemical mechanical response, and represent a deformable granular matter as well here. Right? So those are the examples that will show that highly deformable granular material are important here. And then here's their behaviors, how it matters. And on the left figure, I show that how a typical green powder, and in there, for example, the tablet can be recompressed, and then you can see that the powder itself during the compression process, it can be deformed severely, and then develop multi contacts with the surrounding particles, and then it also can involve different physical processes, including thermochemical, mechanical, and even other processes as well here. Okay, and also it can develop fracture and crushing. So those are things here. On the right is another SEM image of the surface of this alumina and copper compact here. Okay, and these are the process that basically you can really to compress the powders of both metal powders, and then with certain kind of like heating, and then you can form certain alloy thing for that here. Okay, and so in a sense, these granular matters are highly deformable and have an important industrial application here. Right. So um, uh, in the past, how we can study and understand their behaviors of this highly deformable granular matter, and we can use experimental tool, for example, in the laboratory scale, that we can use this dye compression or its traction compression test to test their macroscopic behaviors here, right? Or we can use a more advanced microscopic equipment that observe, for example, single particle compression, or we use photoelastic experiments I mentioned before, or use the DSA, digital imaging DSA equipment really to observe their to measure their trajectory there. Okay, we can use CT tomography really to emit their compression process here, right? So intuitively, and the experimental way that can give us quite intuitive observation and how this granular matter deformed, and how they develop multiple contacts and then connect each other. Later on, naturally, a lot of powders they have when they develop contact, there'll be cohesive force to connect them together, form certain strengths here, right? Okay, and then the experimental tools allow us really to test the performance of those matters in a larger scale, and the resolution is limited by the specific devices that we use here, right? And so sometimes if we want to have a quite detailed observation of the individual contact level at the grain levels, and then sometimes it can be quite limited here. And so those are experimental ways. And then numerically, there are three ways really to study the multi-scale behaviors of the deformed by granular matter. And so traditionally, people use continuum approach, and then, for example, they use the FEM, and typically to study the deformable granular matter. And as shown on the left and right, those are the 2D and 3-dimensional FEM, and to study that when we do a dye compression or other kind of compression process, how would the stress strain relation or the density evolved during this compression process. And this continuum approach normally will give us a relatively high computation efficiency, and we can simulate a part levels that scale, and then to really test the performance, which can directly be used for practical design. Okay, but there will be a very challenging really for us to observe the particle level phenomenon. That's one drawback by this continuum approach. And while the discrete method, and then we have introduced quite a lot. For example, DM is one thing, and also other methods where I'm going to show later that can be used. Okay, and then these are the mechanical approach that we consider in each individual grains, and then and model a realistic number of grains, and then to look at their interactions, and then sometimes but it's numerically it's relatively challenging, and we need to develop relatively more advanced strategies to deform highly deformable grains. Because there are certain progresses like this work, and led by Dr. Gonzalez, and I guess is in Purdue, in Duke University, and then they developed this bounded particle, and then to simulate the deformable deformable granular matter, okay, to study like this tablet compression process here. But as I mentioned, this is ongoing research area that representation of this powder grain deformation, especially light deformation, is a challenge by DM alone here. And so the third method that now has become popular is called hybrid method. Similar to what we mentioned, this like multi-skill modeling approach we introduced before, and it's specifically similar to what I mentioned before. It's called FDM. And here the hybrid method can be represented by one method is called multi-particle FEM. These are the 2D or 3D examples shown here. Each individual grain, and we consider that a grain particle, powder grain, and each grain we discretized by finite element mesh, like on the left, and on the right here, and then we do all kind of testing, compression, 1D compression, the die compression, or isotropic compression, and then to test how dense we can compare them together, and then test the performance here, right? Okay. In this way, because we resolve each individual powder grain and by FEM simulator their deformation, stress-strain relationship at the contact levels, and then we can really see relatively high accuracy of the deformation. When we can capture their deformation behavior relatively accurately, okay, and but you can tell that this so-called hybrid method, and we need to discretize each individual grain and by a lot of number of FEM mesh, and then the computation efficiency can be low, right? Okay, and also we know that FEM mesh has a lot of issues, as I'm going to show later, and then when we really to compress some particles in a severe deformation patterns, and then the FEM mesh can be extremely distorted, and it has a mesh distortion problem. Okay, because mesh distortion normally will cause a numerical issue here, right? And so these are the hybrid discrete and continuum approach that that we can use here. Okay, so to summarize the major computational challenges in simulation of highly deformable granular matter, and the major issue is that each individual particle may undergo very large deformation. So we need to capture that behavior in a reasonable way. Reasonable means that both accuracy and efficiency should be balanced. And also, because of this large deformation of each individual grain, and then their contact is no longer like a DM. You have a single or a limited number of particles between two particles. Okay, and then their contact is evolving because the contact area can change from point contact to line contact, area contact. Okay, and then with this contact area changing, and the frictional behavior, of course, they are cohesion as well, because the powder particles, the grain powders, and then normally because their particles small and their physical chemical properties make they can develop certain absorption forces and attract each other, develop cohesion. This is indeed a desirable properties of this one. How we really use this property to manufacture the tablet and other things here. Okay, so the deformation and evolving contact and will affect their friction and cohesion and overall behavior here, right? Okay, and so that's a third point that we need to be able to model the large deformation and cohesive behaviors of each individual granular particle here, right? Okay, and this is also if any physical process involve multi-physics. Okay, for example, we want to do heating, and in the meanwhile do this die compression. Okay, and then we do centering and do compression in the meanwhile, and then we need to consider that multi-physics as well. So those also pose challenges for computation here. Now I'm going to show several approaches and really how we going to handle one or several of these challenges listed here. Okay, and first method that I'm going to show would be this multi-particle FEM. But you can tell from the name shows that multi-particle FEM I showed before. Indeed, this is what we do here. This is one indeed example that shows the multi-particle FEM. This is not a new method. Okay, so the first step I want you to use this a method that to show that how we can understand this highly deformable cohesive granular matter better. And so the method itself follow a very standard FEM approach that we can assume relatively simple elastoplastic model for each individual deformable powders, and then that model, for example, isotropic hardening and use surface model, and then to use to describe to put this Gaussian integration point of each mesh in FEM here. Okay, and also we want to consider the cohesive behaviors here. Okay, when the two particles approach each other, okay, for example, these are the two neighboring surface of two approaching particles here. Once they approach each other, and then we assume there will be a cohesion developed. Okay, and then this cohesion, well, we use certain kind of cohesive law to describe that here. Okay, and then when we want to polter a way that we need to overcome this cohesive force here, right? Okay, and then so at the contact level, and you could also develop if the compressed develop contact force that's the same to the DM, but meanwhile for this cohesive particles, we also consider that they have cohesive force here. And then if the pulling force is sufficient, and they can separate at the surface, at the interface, and then break. These are the formation and breakage of a cohesive solid bridge between these two contact forces here, right? Okay, and then so this is the stress-strain relationship that the normal and shear model that are traction separation law at the contact level here. Okay, we consider tension and compression for the normal mode. Okay, consider a damage initiation, and then with a exponential damage evolution law here. Okay, and then when they unload, and we assume that they last unloading here, right? And then for the shear mode, and then we follow quite a similar model patterns here, right? So these are we also consider the cohesive contact here, in addition to the normal like in the Hertz model or Hertz-Menden model or these other models here. Okay. And then these are the as I mentioned that multi-particle FEM, and then for each particle, and then we discretize each particle by a lot of finite match here. And then first that we want to do some validation and calibration here. For example, now we consider quite a simple model setup. We consider two spherical particles. To save the computational effort, we cut each particle into half, and then we let them to develop a contact, and then we test this results here, and then to compare it with the analytical Hertz contact model here. Okay, we do loading and unloading. So we do loading to this level, and then we do unloading here, and then do this loading. And so these other false under overlap relationship and compared to the analytical solution here. Okay, and now we can really test the different fracture energy equations, and then to test this elastic to consider this JQR elastic, and then also consider compared with this Gaussian here. When we do this loading and then do unloading and then do these are the normal contact force and normal overlap here. Okay, and then when we do this unloading, and then you have this curve because you need also to overcome that certain other the cohesive force here. So here we consider both Gaussian. These are the black one is the Gaussian here. Okay, and then when we do this unloading, we consider the different cohesive force in this JCAR solution here. So this serves as a validation for these examples, right? And as I mentioned, probably some of you ask, and see that this FEM seems so dense that you serve the very good one. And so when we want to simulate a particular example, there the mesh density can be a matter indeed. And so that's one of the issues that we have to deal with. For example, when we consider a assembly wanted to compact it, and then before that, we wanted to do a mesh sensitivity study. Now for each green, and now we discretize by different mesh size. And this is a relatively coarse and finer, even finer. This is the finest here. So this is a typical mesh size that we use. We use 4 different mesh, and then we do this mesh sensitivity study. And then with the mesh become finer, and then the response will gradually converge up here. Okay, of course, I mean, by the end, it's still you have room to improve, but just for demonstration purpose, in the isotropic compression, that it will converge to certain kind of like identify stress strain relation, stress density relationship. And in the following study, we're going to choose this finest case just for demonstration. So you can do mesh sensitivity study, and then this is what we call numerically we call a consistent study. And then you choose a acceptable set of mesh for your study here. And then these are the finest mesh case that when we do isotropic compression, and then the sequential deformation developed at the beginning. You have only have certain particle deformed here, and then there will be more deformation and deformed in more particles. And some more particles, this red area, sorry, I should have put a legend here. Red area, this is indicated that there will be plastic deformation, plastic stress developed at its contact levels, and then these are the more plastic deformation occurred here. So those are the von Mises distributions during this compression process that we use this multi-particle FEM here, right? Now let's do a formal analysis, use this model to do powder compaction here. So these are the model setup. There we use a total of 329 sphere particles, and each particle was spared by the finest mesh that we showed before. And then this will total have a 1.6 around 1.6 million tetrahedral elements in play. And then we load it in a rigid cube here. Okay. And then this sphere particle have a grain size distribution between 0.055 millimeters and to around 0.0995 here. Okay, these are the model parameters we used here. So the precise data we randomly packing and generate those particle by DM. In the DM have a quite a very good weight for the particle generation. And then we imported that DM generation packing and into our FEM. Indeed, here we use the commercial one, use Abacus. And we import into Abacus, and then we we gender match for each individual grain, and then we build such a FEM model here. And those model parameter has been selected from for both the elastic model and the cohesive content model. And the model parameter is reported in the literature, so we just directly select that for the study purpose rather than for generative elastic behaviors here, right? These are the process how we compress. And then you can see first we do isotropic compression, and then there will be plastic strain generated and shown by this von Mises stress, and at both the surface which is in contact with the rigid wall and also in between the particle here. And we render the surface of the particles become severely flat, okay? And then once we stop the compression, and then we can remove the pressures of remove the walls. And after removal, you can see it have a certain instant rebounding. We call it elastic recovery here. Okay, those recoveries it because the particle itself not only cohesive and deformable, but the deformation also developed at contact will store the some certain amount of elastic energy, and this energy when you release the external force, and the energy will be released out, and that generates the so-called elastic recovery. Okay, and then we can define this one by such we use an index to define that, and define the ER as a maximum relative density during this loading, and minus the minimum relative density. It refers to at zero pressure during unloading and divided by the maximum. And we use this normalized quantity to refer this so-called elastic recovery here. Those are the curves that we observed here. Okay, and so the elastic recovery changes observed that increased with the maximum relative density, but there's a bending point where at a certain maximum relative density, and when it's below that, and this slope is relatively small. And then after that, you need a higher, we observe a higher slope between this one here, okay? So this change of slope for this so-called bilinear relationship in our simulations, okay? And so this density is around 0.86, okay? This is the underlying mechanism is the dominance of this stored elastic energy and the effect of cohesion. Okay, so there's a competition between the two parts. Okay, and so for example, if you have a higher relative density and the elastic stored inside elastic energy can be high, and so that rebounding will be stronger than the cohesive force that want to pull them together. Okay, during this compression. But when this relative density is low, and then the cohesion will more or less more dominant than the stored elastic energy for the rebounding here. So this is the way that we observe from this from simulation, why the elastic recovery. Okay, and this is the one of the properties that we want to understand about this highly deformable particle here. And then another thing would be this the elastic how does that change with the particle individual green Young's modulus? Okay, and we find that we observe a nearly perfect elastic relationship between inversely proportional linear relationship with this elastic recovery with the Young's modulus of the particles here. When the particle is relatively softer, okay, and then we have a higher elastic recovery. when it's relatively harder, then it's gonna be have a lower recovery here. Okay, indeed, we can really to do in our study, we have a paper published on this one. In our study, we can further extend, for example, if our Young's modulus becomes so high, just like a rigid body, we can extend to certain limit, right? Okay, and so that only the cohesive force matters here, right? Okay, so that is what mind you that this plot in the log llama here, okay, in log logus plot rather than a natural plot, like natural scale here, right? So that is related to how the modulus of each individual powder grain will affect this elastic recovery here. Okay, and further we can really analyze the elastic strain energy here. And so we plot the elastic strain energy evolution at a different relative density. And the relative density is monitored during the compression process here. We compress the loading, and then we see the relative density will be increasing. And then when we do unloading, and then it rebound, and then first rebound in a quite a steep way, and then will become flattened, and then in this way here. Okay, and then different Young's modulus of the particle, of course, will affect different rebounding process. The softer, and then the particle of the rebounding will be unloading process will be more significant, and then there will be more elastic strain energy released here. Okay, but the stronger will be less here. Okay, so the total elastic energy, so electric strain during this loading stage related to the elastic property of the grain itself here. So those are the elastic strain energy, and also we can look at the so-called residual elastic strain. Okay, and then these are the similar plot at a different Young's modulus, and then this is the residual one, and how we really do a loading and then do unloading to look at the residual strain, and then as assembly that we observe that is tend to be to similar, and then in patterns, and then of course will affected by the Young's modulus, but their pattern is quite similar from the simulation. And also we look at their overall Young's modulus. Here the Young's modulus is not the individual particles, and so we distinguish two Young's modulus. One is the individual powder grains, and the other is the overall assembly here, right? Okay, and so what we do is we have a three-stage loading to determine the overall assembly Young's modulus. We do isotropic compression. We compress this assembly isotropically, okay, and then we do an isotropic unloading. We gradually relax the compression in all directions and to certain stage and close to zero but not zero. And then then because here remember our assembly and has been developed a certain kind of cohesion, right? Okay, this cohesion is not totally it will be formed during this compression and loading process, and then now this become a cohesive assembly, and then we can do a unconfined compression. It's basically uniaxial compression to test their modulus here, right? Okay, and then this is the process that during this unconfined compression, and we determine the Young's modulus at a certain initial stage, okay, to indicate that is during elastic thing here, right? And so that is the results that we get here. So the relatively elastic modulus we determined show a relatively linear relationship with the relative density here, right? Okay. And also we find that when we change this fracture energy relative fracture energy GC, that refers to the cohesion model, cohesive model that we mentioned before. It has such we can use such exponential relationship to fit their results here. Right? So those are the testing results that are how we can determine the Young's modulus of the assemblies and then form the individual particle levels for such assembly here. We can further look at the damage behaviors of the samples. Again, that we do this loading. We first compress it isotropically, and then we do isotropic unloading and compression, and then we do this kind of uniaxial compression. Okay, and then we test the different case of cohesive force, and GC means this the fracture energy that we can develop to break cohesive force part here. Okay, and so the behavior is relatively similar here, right? Okay, and then these are the other simulation results we can do on the top. On the top, and we at the beginning at here, and then we do isotropic compression, continue isotropic compression, and then this is we do isotropic compression, and then we do isotropic unloading. This is isotropic unloading. After that, and then we apply vertical forces on top and bottom, and then we actually compress it, and this compression will generate damage here, right? Generate damage here, and then some part can be totally the cohesion can be totally removed here. Okay, and so those are the von Mises stress, and the bottom is use another features to see just the damage, the so-called damage that. So here, those are the deformed permanent deformation. We means that when we really disintegrate the whole samples and then to different part to show these are the final forms, and this serves damage. We use just a damage variable to indicate it. Okay, and in the process here, and then we can also develop use a Rishkovich and Duckworth equation to describe the stress and with a porosity here. We want to develop a extreme case, for example, the uniaxial strength of the compactor in essential is going to be increasing exponentially with the maximum relative density. Whereas these are the samples we do here. Okay, and so these are the uniaxial strengths we tested, and then these are the relative uniaxial strengths we developed, and these are the maximum relative density, and this is the curve here, right? Okay, and then the dashed line is the fit of this equation for the description here. We could also use another kind of equation proposed another scholar, but their fitting is less desirable than in this case here, right? Okay. We also found that the contact surface area can be correlated with the uniaxial strength in a linear way. Okay, and also the correlated with this thing, and both the relative density and the packing and the fracture energy of cohesion have similar effect. Here, this is fracture energy of the cohesion, and have a monotonic relationship with this uniaxial strength exhibited by the thing here, right? And then these are the testing of the strengths of the packing here. And that is uniaxial compression. And then we want to further look at their behaviors under traction compression here. Okay. And again, that we are doing this process like we typically doing it in the cell mechanics, that we isotropically compress a assembly, and then we do isotropic unloading to allow certain remaining bond or cohesion develop. And then we do traction compression. So-called traction compression just show that for those who are not with a laboratory test, that when we do traction compression, we can really to confine the samples, but add certain larger forces or larger stress in certain directions, and really to create a shearing or divatomic stress. For example, we apply more force along the vertical directions than the horizontal, and this will create a condition here, right? And then, so this is the plot, stress path. We first do from zero stress state, and then we do isotropic compression, and then we go back, do this isotropic unloading, and then we follow a traction compression line here, okay? So those are the traction compression, and those are the response that we get. First is the typical stress-strain relationship here, okay? And then at a different maximum value density, that we basically develop a hardening behavior here, right? So this show a hardening behavior here, right? And the volume is typically is contraction and this compression here, right? And then higher relative density will have higher divatomic stress as I show here on top here, okay? And then the volumetric contraction on the right show that their the higher relative density and then the less contraction that exhibited in there. Right? So those are the traction behaviors we observe here. And then we can further look at the divatomic stress, and when we develop here, we only we look at the how if we change this fracture energy of the cohesion, how does that matters. Here we have a control case where we do not allow the particle to develop a cohesion. So the fracture energy is zero for this case here, right? And then you can see here, it gives us a compression hardening and peak and then softening behaviors. This is typically we observe that in for granular matter. Okay, if the energy is small and it can still exhibit a similar case, but if the strain fracture energy is big enough, and you can continue observe a cohesive behavior, a hardening behavior here. Okay, and this is quite similar to to some kinds to sand. Their loose sand and dense sand relatively have different behavior here. For example, here the volumetric strain evolve with actual strain changes here. This non-cohesive case give us a quite a typical contraction and to dilation curve. It's quite like a dense sample, and we will first have a contraction, then dilation here. And then if you have certain cohesion at these levels, and then this will be delayed. So the dilation will be delayed here. And then if the frictional energy is the cohesion strong enough, and then you will only exhibit a contractive behavior here, right? And so that is a thing that we can relate to examine and then to understand the difference of this highly deformable and cohesive granular powders and under traction compression. How does that differ than a cohesionless hard particle like sand here, right? And those are the cohesion damages that for certain cases that we have shown before, right? That this is for a traction condition here. We can further do analysis that we plot all the data together in one single three-dimensional surface. We plot the divatomic stress, the confining pressure, as well as the fracture energy of the cohesion, and then we develop, we feed such a exponential law relation under for the different part among this divatomic stress with the confining pressure and the pressure energy here. Okay, and then this can be projected for at the box plot that I showed before here, right? Okay, and so this is that we basically want to develop a general three-dimensional like a yielding surface or state surface concept for this highly deformable cohesive granular matter here. And then this is the yield surface we can further plot here. Okay, and then again we can really do different reloading, doing the reloading, and we can make use of the reloading schemes in a laboratory test. We can develop different loading paths. And the different loading paths, when we observe yielding, and then we observe this onset of plasticity, and then we record that point at the yielding point here. Okay, so this is what we do here. But we do stress part, do isotropic compression. This is the mean stress, this is deep topic stress, and then we isotropically compress it, and then to at a certain point, this is isotropic yielding here, and then we do unloading and we explore different curve here. Okay, and the control group that we consider a cohesive zero cohesion case, and then also with certain cohesion. Apparently, that the yield surface without cohesion, and even the particle itself still deformable, highly deformable, is smaller than those with cohesion here, right? And if you look at the same mean stress levels, and these are much higher than this one. It could, the difference can be like 30 to 40%, even 50% here, right? And then in the cohesive case, and the yield surface that no one's can sometimes there's a crossover, and we didn't plot it. And in the low stress levels, and this can be smaller than the cohesion part here. Okay, that or the observation for that part is for the high stress level here. And so that is because the cohesion can restrain the motion of particles and limit the plastic deformation more significantly in the low confinement pressure cases here. Right? And then we can also look at the hysteresis behaviors one, and we do a lot of different loading and unloading cycles, and then to look at the behaviors. Those are the plots that we have done for this one here. Okay, and then we look at how the damage dissipation and then evolved at different cycles here. Okay, and also how the plastic deformation, plastic dissipation energy, we can differentiate them. Okay, at different things here. So the no cohesive strength of the contact and give us typically a solving well. Sometimes the cohesive strengths exist, and then they could give us a certain hardened behavior here, right? So in that case, there also there are two mechanisms here. What do we call the damage? Damage mainly refers to the cohesion, and when we compress it, there increase the contact area, and cohesive force attract them together and then develop cohesion. And then when we shear it and that cohesion break up, that's called damage. But here the plastic deformation refer to the deformation, shear deformation, and volumetric deformation, and developed and leave a permanent deformation for the particle. That is called plastic dissipation here, right? And then that can really attribute the different mechanisms that are both dissipation energy will decrease with increasing cycles, and these are the hysteresis behaviors that we explore the problem. So this is basically we use the existing method, and we even use a commercial software like Abacus, and do certain kind of implementation, and then to try to understand the behaviors. But as mentioned, that we need to discretize each particle by a lot of finite method, by finite mesh, and then you also need to have consistent results. and then that computational effort can be high. And then now we introduce another method called a total Lagrangian SPH. And then the smoother the SPH method is basically a relatively new method that are developed gain quite a popularity in recent years, and then to for large deformation analysis, and also it has been pretty successful and applied to a flow problem like wave problem here. Okay, and either now the formula that we used to describe this deformation behaviors of the mechanical behaviors, we follow a total Lagrangian formulations. Lagrangian formulation means that the observer coordinates or fix certain particles and then do the flow here, and then it can really help us to trace large deformation relatively easier. Okay, and then we could also develop a certain like hourglass control to ensure the numerical stability, and then we use large deformation definitions like deformation gradient to describe the structural relationship. Okay, and then the considered model is relatively easier, and here we follow the existing one reported in the literature. And similar that we all know, remember now here, I wanted to introduce a alternative approach to the previous multi-particle FEM. And I just want to replace the FEM by SPH. And then we don't, with this SPH, and then we don't have really to use to save the computational effort here. And at each individual particle, and then we need also consider the particles. Here, the simple strategy is we can really consider quite similar strategies as shown before. Okay, we consider normal and shear behaviors at individual particle levels, and we can allow contact and also large deformation development at the contact level. Those all can be described with the same framework of this SPH here. Okay, and those are the contact modeling. We consider normal force and friction contact, and each individual particle will be simulated by SPH here, right? Okay, and then we consider linear deformation, linear contact, and failure. Failure can be judged by normal, shear, and tangential, those three-dimensional one here. Okay, and also the cohesion similar that it can develop cohesion, and cohesion can be damaged if we exceed this friction energy strength, and then we introduce a damage parameter similar to previous one, and then to indicate that stiffness called the stiffness degradation during this thing here. And then we combine we consider a combined frictional and cohesive contact model, and somehow this is the bilinear traction separation law, and here we use bilinear one rather than the previous like a exponential softening behaviors here. And then we consider a Collins friction law like this one, and then these are the combined friction and cohesive model we mentioned here. These are the calibration that we calibrate experimental observation and calibrate the model parameter for the analysis here. For the structural relationship, that we use the deformation gradient, and we define such a strain rate and spin tensor, and also we use the Yeoman stress rate to other objective rate, and used to describe the light deformation in SPH here. Those are the structural relationship update algorithms that we used in the analysis here. And also in order to enhance the computational efficiency, that we develop a GPU parallel computing strategy that for the computing for the calculation here. And so these are the we have several benchmarks. One is we consider a cubic packing of these SPH particles, and then we use 12,500 particles for this packing, and then their elastic property and the power law string hardening relationship, the model parameter are calibrated according to some literature. Okay, and we can apply different boundary conditions like bottom with fix it, and then on the top and the other boundary conditions we can apply compression, tensile, or shear for different purposes. And those are the one benchmark that when we do compression and extension, and then how the structural relationship here. Okay, and so these are the tensile as the tension. We apply tension on top. Okay, those are on the compression curves here. Okay, and then we also compare with a pure FEM simulation. FEM basically we use we consider such a cubic FEM domain without particles, and then we just assume the same model and do as a benchmark, right? To do a comparison here. So their curve fit each other quite a while, and also the deformation patterns are pretty much similar here. But what we do is in our SPG simulations, our generated even at the corner is relatively smooth. But FEM, we observe quite excessive deformation just because the deformation is large, and then you can have a FEM mesh distortion shown in the samples. Another benchmark showed here is a contact examples here. And for example, we add a rigid body plate, and then push a particle. We simulate a half ball here, and then downwards, and we do unloading, and then do a loading, and then we remove it slightly and do the simulate this unloading process here. Okay, and we want to monitor to examine the contact stiffness, how the cohesive strength, fracture energy, and the particle spacing affect this one here. Those are the results that we examine the normal contact force, how that would change with the normalized overlap. That's quite similar to the we want to compare with the Hertz solutions, right? Okay, so these are the data. So if we use different contact stiffness, and then how would that approach this Hertz solution here? Okay, this is further, and we compare it to this JQR solution, and then essentially we do loading, and then we do unloading here, right? Okay, and so JQR give us such a curve, and it will be unloaded to 0, but we are going to have a certain overlap remains, and we unload to this point in our simulation here. Okay, and JQR have an idealized situation which is not realistic at this part here. And this is a further examine of this the contact force as shown before, how that affect how would that depend on the strength, and also different fracture energy will affect the behaviors, and also different particle spacing is quite similar to SPG, quite similar to the mesh density, right? How would that affect the performance? We did a consistent study here. Indeed, these are the illustration here. If these are the on the right is a pure FEM mesh, mesh size of 0.01 millimeters, and then now we compare to the given SPG spacing, particle spacing cases, and do a comparison. Now, if we reduce spacing to 0.01 millimeters, indeed it generates a result from size distribution. It's quite similar to FEM, right? And we have done another benchmark. This one is also quite simple, and we consider a plate of this a plate, and we move we basically want to reproduce this Coulomb frictional contact, right? We move this top block, and then to look at the tangential contact behaviors, and those are the generated curves that are simulation results with this theoretical results here. And also, we further compared this one, the two particle contact things, and then because we want to indeed from this one want to examine the normal and frictional sliding contact for the highly deformable one. We compress it and then develop a certain contact area, and then we want to shear it and move the top on right here, right? Okay, and then in our we further compared with the FEM here, and on the left is the FEM results in the literature, and then it showed that when really shear it, because this contact area is large, developed permanent plastic deformation, and also have certain cohesion, and then this can really cause excess deformation and cause numerical instability for FEM here. But we do as speech, and then we can really somehow to overcome this thing here, right? And then now another example is how we can apply this one for the model of compression, and we generate a packing of 2,160 spherical particle grains and to model this die compression here. And then the total SPG particle, these are the grain, and each grain is simulated by a certain number of the SPG, and then we want to do the thing. So the idea is quite similar to the multi-particle FEM. And in FEM, we use the FEM to simulate each individual grain here. And now we do this way, and then we run the packing by DM, and then we do this mesh generation of SPH, and then we build this model here. Those are the model parameters we adopted, and those are the die compression that we simulated. We compress it, and then the compression can be significantly further. We can really compress to half height here. These are the monitoring energy and change with the relative density here. And then these are the further solid fraction of the function of this compression pressure here. Okay, and so the relationship is somehow can really give us an insight about how the plastic deformation developed at a certain stage, and then during this decompression process here, and also we can monitor the energy and the density here, right? Okay, and then indeed, and then there also we observe certain particles there's a rearrangement. Not only you have you can develop a sliding certain point contact to accommodate the deformation. These are the further results. We plotted the distribution of the contact force magnitude, okay, to consider a cohesion or a pure frictional one, and then also to look at the change of this thing, and then we follow a probability density function for the normal contact force proposed by Farhan Raja, and then to fit these things. And here also we define a fit index for the pure frictional case and for the cohesive case, and then to monitor results. Our results show that the PDF of this normal force can be nicely fit by this the theoretical model. Okay, and then in the cohesion part, the cohesion can cause more uneven distribution normal contact, because you can imagine the cohesion developed during this compression process will prevent the sliding, right? And then there this will generate uneven normal contact force distribution here, right? And then at a relatively high density, and then the sample can become unstable in certain cases here. That is we use a total Lagrangian SPH to model the behavior here. Now I want to show another extension that for the total Lagrangian SPH, and we have demonstrated that we can use that to simulate, to replace this multi-particle FEM to simulate the highly deformable cohesive granular matter, which is a mechanical modeling of this granular matter here. Now we want to look at other things. For example, we want to see that the thermal effect and how we couple thermal effect into this thing. And then we know that the total Lagrangian discrepancy is not very convenient to describe the flow behaviors, and then similar to fluid flow, and then the thermal conduction, okay, and heat generation. And that's why, and then but relatively the Eulerian descriptions is quite convenient for that purpose. That's why I wanted to, in the same speech, wanted to couple this total Lagrangian formulation for the mechanical behaviors for deformation of the particles, coupled with that a Eulerian description for this heat generation and thermal conduction to simulate the thermal mechanical behavior of this compression powders. Here, these are the fun details which I'm not going to go to each questions. Here we for the considered model and the heat generation for the mechanical part, elasticity, and we use the Johnson-Cook plasticity. And for the heat models, and then we consider that are different heat source models, and then to do the heat conduction one here. Okay, and these are the stress update schemes, and then these are the stress yield surface demonstrate. Those are the flow chart for the whole coupled speech framework, and also we further use this GPU CUDA acceleration. And then first we do a validation. The validation again is quite similar, and then because there's no we benchmark with a FEM model with using the same using the same model, and then with this as pitch, and then these are the shear and the tensile test, compression, and these are the tensile ranges, and then we observed and compared with FEM. Okay, and of course here we consider a temperature, the different temperature levels, and then for this compression here. These are another benchmark. Is like a 1D thermal conduction problems here. We have a column, we have a bar that we hit on this end, okay, and to look at the temperature distribution here, and then here we have one case that we set a temperature on the boundary on the left, and these are the comparison with this analytical solution. These are now we set the heat flux boundary on the left here, and on the fixed flux boundary, and then we further compared with another analytical solution as a benchmark here. Now let's look at now this use this coupled total Lagrangian Eulerian speech, how we can simulate a thermomechanical behaviors and do this decompression. Quite a similar model. We compress it, and so these are the thing. And during the compression, and we see that the compression can generate change the temperature and generate a heat. Okay, and so for example, you can really see that the plastic deformation can really to oscillating generate a heat. Okay, and so this is the thing that we can assume one of the things here. Those are the micromechanical response that we see that at a different room temperature, at different environmental setting, that how the deformation can be developed here. Okay, and so indeed that this loading curve will become have a higher yielding strength, and when we have a lower temperature. So high temperature will give us tends to give us a relatively small yield surface. Okay, and so that's why what do we get here? And also this is a further plot of this normal contact force. Again, that we use Raja's systematic model for feeding, and those are the change of this the parameters with the different solid fraction at different temperature here. These are the further frictional behaviors that we plot the friction in the of the sliding index and quantify from the sliding and normal contact force for all the contact surfaces that are plot the probability density function here. And also we with SPH, and then we calculate to quantify the shape effect here. For example, when an initially spherical particle and when they deform and become different sphere shape, and then we calculate to analyze quantitatively their shape change here. We can use this Minkowski shape functions and to quantify the shape and plot the probability density function and other shape parameters here. Those are the things that we calculate to generate a so-called convex Hall to really to calculate those things here. And then we can also really to simulate using this thermomechanical model to simulate this sintering process here. Okay, again, there for the sintering process, probably we need to have a refined consideration that for the thermal contact problem, we need to consider the heat flux boundary here. Okay, and then we calculate the heat flux inner, we have different particle, and then they have different temperature, and then there'll be heat flux developed among them here. Okay, this is like a benchmark. We have two half sphere particles, and then we develop a contact. Okay, and one is a higher pressure, and the other is lower. Okay, and then the hot one will transfer the heat over to the bottom here. Okay, and those are the we can really to compare this effective conductivity, conductance, and with the conductive force relationship, and compared with this analytical solution developed in the literature here. And another benchmark would be a imperfect thermal contact here. We have two kind of materials that they have a different thermal conductivity. For example, when we at the interface, and then when we apply different temperature, there'll be thermal conduction, and then this is how the temperature changes during this one, and then during the conduction process, and with the time here. This serves another benchmark, and we further compare with the FEM simulations as a benchmark example. And then now, when we look at the sintering here, and then this is a simulation of a packing of 167 spherical grains, and the grain, each grain will contain a lot of SPH particles, and make the total particle like this one here. Okay, and when we compress it, and then these are the contour of this the temperature as well here. Okay, and then so we can monitor the evolution of the pressure, and then during the loading, and we can also do during the unloading the process. How would the sintering temperature change the behavior here? Right? And then we can further analyze the stress distribution here. And then we find that the von Mises distributions during this sintering process can really transform to a Gaussian distribution here. And further, we can analyze in detail of this contact force, which I will skip that part, and the grain shape analysis similar like before here. And so along this line of research, we can further look at other manufacturing process, like when we do the pharmaceutical tablet decompression, and then when we remove this cap of this dye, and rebounding will normally will cause a so-called top punch, and then that is something that is interesting to the pharmaceutical industry here. And also we can also use the machine learning method for this compression loadings. And there are also other scenario that we can apply this line of research. For example, we study this electrode manufacturing process, and to look at the performance of this battery. And also we can look at the formation of the sedimentary rocks and how to understand the geological behaviors of that. And also we can, because we see the deformable granular particle, we can also look at the cell growth, or we can look at the flood, or how this flood cell and transport in the vacuums in that kind of processes here. So as advised by Professor Wagner, and we're not going to have stop, because I will going to continue in one go to finish all my part. So I will go on. All right. And so I will continue with the second part, how we can model continuous green crushing. Okay. And quickly go through that. In my own opinion, that there are two major challenges in granular meter modeling. One is green crushing. Okay, in the individual green, and there extensive in the individual green crushing individual, there are a lot of study already, and it related to a lot of engineering process like this in geotech engineering. And when we do pile driving, and the pile can ready to crush the surrounding sand particles. Okay, especially for example, if particle is weak, like this coral sand, and then crush a lot. And in the salt and powder production, we need to generate fines, it's crushing. The mine and the minerals, when we crush, we have this crusher ready to create this product. And when we generate fertilizer and the food grains, and then crushing happen a lot. Also in the earthquake engineering, when we study this fault gauge, and then this part, because the shear and compression is huge, is high, and the crushing can crush these particles into fine particles. Another challenge would be the grain shape. And then, natural sand that we have quite a variety of different shapes. And these shapes, how to describe the shape mathematically and mechanically, and model them is challenging here. Now, if we combine the grain crushing and the grain shape together, they pose a combined challenge. Mean that there will be interplay, because the shape will affect the individual particles crushing, and when we crush, definitely the shape changes, and then how we really model the interaction in assembly will be challenging here. Okay, and so this interplay between this crushing and shape will cause a you have really set a evolving crushing criterion. You get grain size changes, grain shape changes, and then they'll affect the subsequent established contact and force distributions, and then will affect subsequent crushing here. And you can tell the physics is quite complicated, and if you consider eventually consider both aspects in a realized way, right? Okay, and that is what we this is what in the literature people have done, and people either use this clamped particle, and you clamp identical sphere particle together using use a bounding model, and then to do all kind of mechanical test to cross them here. And apparently, this is quite similar to what we have presented before. You need this computation is quite expensive. We're going to do that. Okay, and also there is essentially these are the approximation, right? Okay, and then the crushing behavior and the size distribution is not as realistic. The another one is called particle replacing method. and we all use a spectral particle. And then when the quotient criterion met for certain particles, and then we just let them break into a number of small particles with a certain grain distribution and replace them at this position here. So this is called replacing method. Third one is called FDM, is what we see that are similar to the multi-particle FEM. And then we discard each individual particle by FEM mesh, and then we let it cross here, right? And so in the following, what I introduced would be my former PhD student, now associate professor in Kyoto University, Dr. Banju. And so in his PhD thesis, he developed this hybrid aerodynamics and non-smooth contact dynamics approach to simulate the crossing. And by respecting both the grain size distribution, grain size evolution, and shape evolution. So cross and shape will be fully coupled together to capture the behaviors in a more realistic way here. So the non-smooth contact dynamics is different than DM. And so simply put, so DM is a soft contact concept. We allow certain kind of like deformation for each particle, and then according to their overlap, and then it can develop contact force. So this we can use linear contact or Hertzian Menden contact to describe it. But this non-smooth contact dynamics is hard contact concept here, hard rigid, and so they won't develop a deformation. They have this collision and collision reaction force for that, and then they use non-penetration constraint, and then also consider the Coulomb friction, and use the penalty method, and then to do this optimization kind of solution here, right? Okay. So essentially, it's hard contact versus a soft contact with DM. And then non-smooth contact dynamics has been widely used in other field, for example, in the game industry. And a lot of games has been really to they want to have a physics engine and to make it look realistic but more efficient. And then they use this NSCD here. And so popular one, and then for example, those are things that all use this physics engine. And physics library, a bullet, this a bullet or chrono engine are the typical based on this non-smooth contact dynamics. And so the advantage is that computational wise is quite efficient, and this will be quite desirable for crossing simulation. And also the contact force calculated by constraint rather than overlap. And then in this way, it's very hard possibility to handle the changing shapes of the during the crossing for different particles here, right? Okay. And but there's drawback or there's a cost. And the trade-off is that the accuracy is relatively not as DM, okay, but there's a technical that we can improve it. And then now what we do is we use the parodynamics, another approach related to that is for many assembly levels simulations. For the crossing of each particle, and we use the parodynamics. This approach is a continuum-based and non-local approach. They discretize a particle, for example, by many material points, MP here, and then we establish a bond between these MPs here. And this this material point will interact with others within a horizon. Horizon is like a circle, certain, and then they develop different models like ordinary state or non-ordinary state, and then to do that here. And parodynamics or PD has been widely used for a lot of fracture problem or damage problems shown here. And then the basic equation is in the integral form rather than a PD form here. And you can develop a parodynamic force with deformation, and then to calculate dilation on the part here. Okay, and this is a typical ordinary based parodynamics with a linear parodynamics solid model. And also the bond can be broken, and we can use this critical stretch damage model to describe, and then when reached to this strength, and then the strength can be calculated by this critical energy release rate of the material, and this is indeed the physical parameter, and then can broke, and then so it's quite brittle, the brittle feeder model here. Once one bond is broken, and the load will be redistributed to other particles in the surrounding here, and this will, for example, if this part is a bond broken, and this generates a fracture, and this fracture will further propagate and then to generate a surface of fracture surface. Okay, and we essentially couple these two methods together here, and we use a non-smooth contact dynamic to simulate one assembly of this granular material. Okay, and to in a similar way like a DM here. Okay? And remember, this is a rigid particle contact and frictional motion here. And then from the calculation, and then we can develop a certain criterion to see that which particle or what particle is satisfy the crossing criterion. And once it's satisfied, and we take it out, for this particle we take it out and to this PD dynamics, and but we retain the initial contact condition if it's surrounded by 3 or 4 contact, and then we apply same content to these particles, and then we run this PD simulation at same contact levels and forces, positions, and then to verify whether or not it break. Once it break, and then we return this child particle, broken child particle, and put it back in the position of this original particles, and then to let it establish equilibrium position and do this in a sequential way here, right? And so essentially we use this we use a project kernel for this NCSD, and then we use Sandia National Labs paradigm for this paradigm simulation here, and we develop this geometric computational library and to establish to return the crushed particle shape and other things here. Now we look at the single grain crushing. In the literature, there are quite a lot of different crushing criteria, including what I listed here, like this OSS, maximum contact force, mean principal stress, major principal stress, or maximum tensile stress or breakage energy. Things all been reported in the literature, because there are some also did some experiments. So what we do is indeed what we have done, that we found that this maximum contact force, we verify maximum contact force, and it can be one of the best way, because it's basically we want to have a consistent criterion that no matter how many contact in whatever conditions, this one can be used. And also remember, this only is a crude screening. We want to see that a certain particle it met the crushing criterion, and then whether or not it crush, or what are the specific crushing patterns, we let PD ready to run it. So we want to have a very robust crushing criterion, and for our simulations, we look at a single particle under uniaxial compression conditions. We use PD to simulate it, and apply this compression, and then to crush it. These are crushing process. These are PD simulation with some actually CT experiments observations. And this is the other. If we confine this particle, the same particle, under multi-way compression, and this is basically mimic the multiple contact situations when one particle in assembly, and then we load it, and these are crushing behaviors, and essentially there'll be 3 pieces crushed here. And then now we want to verify out of these 6 feeder criterion, and if we have different contact numbers, okay, or coordinate numbers, and then which one will give us quite consistent. So those changes with contact number is not desirable, because it's not robust. And then we find that MCF maximum contact force criteria and this major principal stress criterion are quite consistent. We can use either way for to check our crushing. And that's why we in the following we choose this maximum contact force. It's easy and it's for screening here. And also the crushing band paradigm, and we need to handle the post-crush particles here. Okay, and when one particle crushed and then crushed into different pieces, and then we can really use this so-called CGML, and so we need to do some approximation. These are very fun pieces, and then if the volume content is smaller than certain one, and we are not going to disseminate all small pieces because computation-wise is very expensive, but we return their mass to the big ones, and then we just discard the small ones here, right? And so we still assume that the mass is conserved here. And then, but we also consider that certain approximations, as I mentioned here, and this is the way use this CGAL, the computational geometry libraries, and then to reconstruct the shapes of the child particle after crushing here. And also we know that the particle strength is there's a certain statistical laws that we have observed. So-called survival probability of a particle changes with size, here. Okay, and then that changes so according to experimental test, the formula Weibull distribution here. Okay, and then so this is the Weibull distribution that we we followed here. Okay, and then we use this linear approximation for this particle strength here, and then to assign a statistical strength for this one here. And then also if we assign initial strength for each particle at the beginning, here we use these Weibull distributions for this survival probability. And then when they break here, child particle will be stronger. We know that this so-called size effect, the smaller the stronger here. And then we assign a refined strength for each child particle and make it stronger because their size here, right? And we according to this way, according to the literature here. And so these are the statistical considerations that we done. And so some validations. First, we validated against the test performed by Nakata and back in 2001 on silica sand. And they we reproduce 615 spherical particles, and we compress it to an ultimate load of 30 megapascal in a 1D compression test here, right? And these are the simulation process by this coupling method here. As you can tell that initially 6 spherical balls, and then gradually and somehow was crushed, and then this crushing generated by paradigm and put back in this non-smooth conic smooth dynamics, and then when they cross, they will fill the pores, they do rearrangement, and then develop new conditions and make other particle continue to crush here, right? So those are the other situations that we do, and then this is recap the crushing process. On the right is a number of particles generated through a process from initial 600 and then to 25,000, around 25,000 to this 30 megapascal levels here. This is the further comparison for this 1D compression, and then this is a green star distribution, evolution of green star distributions, and in experiments, and this is our simulations here. This other compression curve in terms of this bond ratio and vertical pressure, and so this is our simulation, and these are these experiments. course, there's some difference, but generally the trend works with each other well. And because also our particle, we simulation the sphere, the silicon sand even is rounded and it's not perfect sphere. Okay, and so there are the differences here. And also, we look at the so-called fractal size distributions. So according to Turcotte, and then there will be a so-called scale invariance. Okay, you see here, and then initially the number of particle, and then with the size changes is uniform at the beginning, and when you cross it and way to develop such a curve here and tilt it, and then there when further cross it will evolve in this way, and then by the end at the high pressure you'll develop this like a solid line here, right? This distribution, and then according to Turcotte, there are a number of particles which is a size greater than the certain threshold, okay, and will follow this power law. And this power law have a so-called dimensionless quantity D in then pocket certain values. According to his theory, that D is between 2.6 and 2.7. And then we verify that from our results, indeed it's in between of that here. So this is a fractional dimension, and we verify to this Turcotte theory here. So with these two, and then we can do a quite detailed analysis on how the shape changes during a continuum crossing. You know that in any numerical tools and any computation, any experimental tools, it's very hard to quantify shapes in a continuum crossing process, right? Even in the most advanced XCD scanning. And also for the size distribution, and then when you really don't quantify the size distribution, and then somehow you disrupt the loading process. And then so with our tool, and we can really do this analysis to look at how the shape of the particles evolved, and for the whole packing, how the grain size evolved, and what is correlation here, right? So first, and we also develop certain descriptors. We use the form, roundness, sphericity, and then these are the common shape descriptors we normally use. And so we in our study we focus on the form factor and sphericity as the major shape factors for analysis. Roundness basically very fine and local morphologies, right? And then we define certain descriptors like there's a definition I showed before, like flatness, Fi, elongation is I over L, and the aspect ratio S over L, and also sphericity is defined by the volume and over the surface area here, right? And then these are the things that I show that are different flatness and elongation, aspect ratio, and then we can generate different shapes. I showed it before. And then there's the other evolution of the shape descriptors here. For example, first, the elongation index. And the elongation index will evolve from right to the left, different compression levels here. Okay, by the end, will converge to these levels, and this can be approximated either by normal distribution or by a Weibull distribution here. Okay, and then this other elongation, flattening is quite similar, but this time is evolved from left to right. Again, it can be distributed to a steady state distributed by this normal or Weibull distribution. And so these are the two shape effects here. And then, so essentially, in a general sense, that particle will tend to really evolve from a less elongated to a more elongated one, and to a more flat one, and to a less flat one, right? Okay, and so these are how these figures show means. And also here is the aspect ratio, and again that this evolve quickly to the steady state, and regarding sphericity, and evolve from right to the left. So with the increasing non-sphericity during this fragmentation process. We can also quantify the means of this shift described as using their 50% means, and so they all approach to the steady state at the high pressure levels here, okay, and along with the same pace of this fractional dimension. And so in some way that this fractional dimension can be used as a variable if wanted to describe the certain evolution laws for these shift factors. So this is one thing that as a suggestion that if someone wants to study on the shift factor evolutions and that, probably you can because they have strong correlation, then this one can be used as one of these variables here. And also we can plot all these shapes with different things and develop their clump there into this zig diagram. Zig diagram is a diagram used to describe of the elongation with this flatness here, and then of different thing. And we do the statistical features the shape of all the particles during all the crushing process here. And then Zig basically classify the shapes into these 4 categories. And so according to the combination of these EI and FI values, they do this spheroid, oblate, blade, and follate here, okay, and the 4 regions here. So what do we found that most of the fragment during the crushing will fall into this spheroid, a small portion into this follate here, and some of this oblate here. So these are the observation here. And fragments have both elongation and flatness greater than 5. Okay, so those are the studies here. But we found that the aspect ratio and sphericity is not closely correlated here. Now one can identify the interplay between this shape and crushing. Okay, one first look at the effect of shape on crushing here. So the crushing strength of the particle will change with shape here, right? And with size here, defined by the with the maximum strength defined by maximum counting force. The strength is defined by maximum counting force divided by the square of the equivalent diameter we define here. Okay. And we do a further normalization, normalized by strength under uniaxial compression. Okay, and in this way, it helps us remove the effect of the particle size and statistical strength distribution. So we use a normalized particle strength for that purpose, and then we monitor how this normalized particle strength changes with different particle shape. First one is sphericity, and we find that the strength, the nominal strength will increase. We look at the mean values and the median values, and then will increase with sphericity. Okay, and spherical particle have a perfect spherical particle will have a mean or medium strength close to 1 here. You can see that this is 1 and this is 1 here, right? And these are the maximum counting force. Suggests that the maximum counting force serves as a very good crushing criteria. You remember our normalized particle strength is normalized by the uniaxial compression. That means that the maximum counting force will serve a very good crushing criteria here. And when the sphericity become low, and then the strength will be very small fraction, like even 0.1 to 0.5. It's basically 10% to 20%, 2 to 50% here, right? Okay, of the spheres here. Okay, and so the particle shape play a very important role, reducing the strength of the particles. Okay, so that is one indicator. we can further do this correlation among this aspect ratio, elongation, flatness here, and then also a quite similar trend. Okay? And but the correlation is not as strong as the previous one here. We can also look at the so-called survival probability. So the probability that one particle can survive here, okay, and then with the different shapes here. So I would think that the survival probability of a particle will essentially drop, and with decreasing sphericity here, this curve here, right? And also as well as aspect ratio, which means that one sphere particle is likely to survive the crushing than a non-spherical particle. So this is the general thing, that translation of this observation here. And then when the pressure is high, and then this one the drop faster here, right? Okay. So this is a two observation here. And also we do the statistical of this percentage of occurrence to look at the number of the major broken sizes, how many pieces of one sphere will broken into it, and then we look at their range of the sphericity and parents particles and with a child particle, and we do this number of major brokens, and mostly a lot of them broken into two, and then some broken six here. These are the correlation showed for the sphericity. These are the showed for this aspect ratio here. And then we find that parent particle with a lower sphericity or aspect ratio will have experience less major fragment. For example, fragment pieces will less than 2 or 3 here, and spherical-like particles will have more major fragments here. We also look at other crushing mode. Okay, for example, we want to look at this so-called asperity broken and this major splitting. You can easily look at a aspect breaking, means that the pieces corners can be crossed out, and versus that the particle itself split more or less from the middle. This is called a major splitting here. And these other statistics we get these other aspect breakage, and these are the major breakage, how that probability occurrence, and with this sphericity and aspect ratio. And so both curves give us such a consistent trend that larger fragment will have a volume not less than 70% of the parent things for the sphericity. And then major splitting is defined as the fraction will have volume more than 70% of the parent one. And so you can see here the occurrence will decrease with aspirator for this aspirator breakage, and but for the major splitting, the increasing here. So this is another shift effect. And regarding the shape of the child particle, okay, these are the things that we plot probability occurrence regarding a child particle, their sphericity, their aspect ratio, and then the child particle also have a low or high sphericity and directly correlated with the parent particle. Parent particle have high sphericity, and then the child particle also tends to have a high sphericity. Okay, and then the sphericity in that sense that we consider the sphericity can be used as a better factor to describe the shift effect on the shape of fragmentation. Okay, and then the local morphology on the particle crushing can be important characteristic that when we consider the modeling here. There are also parts that we can analyze the crushing energy here. And then the specific crushing energy we define as the maximum elastic energy per unit mass and in the particle before breakage. And we do normalization, and we normalize by the crushing energy of sphere, perfect sphere with same volume and fraction energy density, the critical energy released rate, and the unit action compression here. And then to remove the side effect from the particle size and the statistical strength distribution here. These are the other statistical results that when we look at this normalized crushing energy and correlate with the sphericity, and so the crushing energy will increase with the sphericity here. And low sphericity and the crushing energy is relatively small fraction. For example, even less than 10% of for the spheres here. Okay, and then so the particle shape on the crushing energy have a significant influence, and then this range of the crushing energy with the given shape is wide here. Okay, which means the crushing energy may not be a very good criterion and for crushing. And we mentioned before there are 6 criteria that we mentioned. The breakage energy is one thing, but it's not actually a good indicator. And similar for aspect ratio and elongation, but not
okay, fine.
elongation.
We need to take feedback. I'm sending the feedback forms.
Oh, okay.
With you, and once you don't.
Okay. So another thing is the relevant to. I wanted to have a quick discussion on its relevance to cell mechanics before I basically finish off. I made ready to close off a little bit early, and then because we started later, and then without a break here. So its relevance to cell mechanics is the thing that we wanted to look at the breakage index and the critical state, the things that are how in a crushable granular sand or granular meter, how does that we can define certain kind of certain breakage index like hardness, like 809 is one, and then we define the area of this surrounded by the fine crushed fine particles with accompanied with the original one, how is it involved, and then we define so-called breakage. So the breakage normally we see that it will increase with the mean stress in such a way here, and then we can further plot a 3-dimensional plot with ball ratio, break index, and then stress, and describe this breakage here. And in that, to study that, we use the same framework, and then to form a 3-dimensional cubic samples, and subject that to a different shearing process in true traction compression. We can adjust the stress at the different directions, and then to crush the particles within this one at different loading conditions. Those are the snapshots that we got that when we ready to during the crushing process. Okay, and so these are the planar cross-section snapshot and the beginning at the initial state, and then when we crush it, you see the cross-section area will increase, and then further increase and have more crushing, and then to the end here, and then we monitor those evolutions of this particle size. Okay, and then we look at the different strain levels, their evolution here, and also we monitor so-called breakage index. We have mentioned before how would that affect at a different B here is a major principal stress, intermediate principal stress ratio, basically defined in some mechanics as a ratio between indicated the perturbation of the covenant stress compared to the major and minor principal stress. It's basically gave a loading foundation here. Okay. So breakage index will increase very fast at low strain, and before it shows relatively steady rate with 1. Okay, it can continue to increase even at a high strain levels here. And like this 60% is still very increase here. This further strengths that we monitor that define the stress ratio, and then so the peak strength, peak friction angle will increase with B and reach to a maximum at around B equals 0.5 here. Okay. And so this is a curve that at B is the peak, and then at 2 end of the B0 and B is 1, and then it's drop here. This is further is a convergence of this. We look at the shape effect and the sphericity for three-dimensional compression show the similar curve that show in the 1D compression. These are the when we ready to do a look at the different B case, they're quite similar to each other here. And this is the critical state characteristic and quite interesting the fundamental theoretical framework in some mechanics. When we look at how crushing affect that one, when we compress sample to 80% of actual strain, and this is the curve here. If we look at the volumetric strain and then strain evolutions, and so when the stress becomes steady, but the volumetric strain continue to develop, okay, which means that even the stress becomes steady and during the crushing, but there's the volume-wise, it does not really reach the critical state yet here. Okay, this is further that we want to if we regard that state as the critical state for the crushable soil, and then we do this the PQ plus the PQ space, and these are the curve we correlated here. Okay. So at the lower confinement here, and then the crushing event is relatively small, but had a higher and then become bigger here. So that's the turning point of the bilinear fitting. Okay. And then this is basically a change of this like this bilinear changing, and to here. This been related to at about 4.6 megapascal case, and then this indicator a volumetric transition from dilation to contraction. And here again, and we plot the breakage index and with the mean stress. Okay, and this increase with constant rate, and when at a certain bending point here. And here is further analysis of the critical state, sphericity, aspect ratio, and then we found that we can generally regard that as a unique relation between the median sphericity and the medium aspect ratio with the mean principal stress at critical state. And then we further inspect this zig diagram and put only for this true traction compression case, and with other material like a lot of crushable material from other planets, and those are the things that we collapse up together. Indeed, they fall into quite a similar spheroid dome as well here. These are the further fabric. We quantify the fabric anisotropy at a critical state for the crushable sand. We find that there is a unique fabric anisotropy, which is independent of the initial fabric and the stress condition for all the B condition here. But different B will give different critical fabric line here. And then this will I'm almost done, but I wanted to just give you a quick show that there are also other applications that we can use the same these strategies for the crushing simulation. And one thing as I mentioned, when we study is Earth fault gauge, and then we want to look at this sliding plan, and then so it's hot, it's high pressure, and it's sliding, shear sliding, and the particle can be crushed. The crush will affect their stick and sliding behavior. This is how the earthquake happened here. So people want to estimate and how this in what condition this sliding, sliding occurs, and that how that will speed or delay the earthquake as one way to study this earthquake occurrence prediction. And then this is the thing that we can relate to look at use this strategy. And then also other application like this rock blasting, and then you can use this a similar way that my group have done that. Yeah, in this multi-particle FEM utilizing a cohesive contact model, the simulation of the solid bridge formation and rupture between particle and surface rely on detailed traction separation laws in both normal and shear directions. Accurate modeling the transition from contact to damage initiation, along with exponential damage evolution, require precise parameter calibration and high-resolution meshes. Given that minor variation in material properties or loading condition can significantly affect simulation results, the model can become sensitive and potentially unstable, and what strategy can be employed to effectively address this simulation and modeling challenge. And indeed, thank you for your question. Indeed, Edmund, what you mentioned is I totally agree with that. And then the formation of the cohesion and the breakage of them, and then that relative in itself between only two particles, it can be a very interesting problem to work on. Not later on, you have a whole assembly, and so we could really develop quite a rigorous model for that, and then to consider that. But today, I just want to really show a capability and a methodology, what kind of methodology that we can really to tackle the problem. So I didn't really show that how we can really to approach the problem, totally solve the problem in such a perfect way here. But what I totally agree with the question. So the second question is the GKR account for adhesion during unloading, and which makes simulation challenging. And the unloading process differs from loading due to energy loss. And adhesive force can lead to oscillation or convergence problem in particle-based method. Accurately capture adhesion effect in SPH require careful calibration and can be sensitive to particle resolution. Modeling hysteresis and dissipation in SPH is complex and may need additional damping terms. Maintaining stability while ensuring physical accuracy is particularly difficult at low confining stiffness values. What approach can be used to address these simulation challenges? Indeed, you refer to one of the validation things that are in our total Lagrangian SPH simulations. Indeed, again, that I appreciate your expertise on this topic. And then what you mentioned is entirely correct. That during this unloading process, because we consider adhesion, and under that is the JKR model itself. But in our simulations, what we do is basically during unloading, because of mechanical relaxing, and then there'll be a certain kind of fracture criterion development, and then with the deformation, and then that can really develop certain things that are during the process, which is not entirely. Sometimes we would see that is physical, is earth water, the real physics is deformed. But again, that
You'll do it now today.
we don't want really to approach the problem in a perfect way, just of the capability. There definitely a lot of effort need to be put on to solve the problem in a more rigorous way. Thank you.